Την καταγραφή, ωραία. Οπότε μπορούμε να ξεκινήσουμε στην ώρα μας. Ευχαριστούμε πολύ, Διονύση. Έχεις το...
Οκ, τέλεια. Χαίρομαι πολύ και εγώ που είμαι στην Αθήνα την επόμενη φορά από κοντά, αλλά δεν πειράζει. Λοιπόν, θα αλλάξω στα αγγλικά τώρα. So, the topic of this talk concerns a set of ideas that I've been thinking about with various people for quite some time now. And the most efficient way to express the collection of ideas I could find is with the title of Gravitational Observatories. The gravitational part of the title is because it concerns theories that have gravity, general relativity, and observatories because it's related to questions regarding how we formulate observables in a theory of gravity. And the reason, there's older work that dates back 10 years with Hoffman and Hartnell, but the recent work got reinvigorated thanks to collaboration with Galante, Manirat, and Beatrix Mollman, who are all very excellent. Damian is a colleague at King's, Chawakorn is a PhD student at King's, and Beatrix is a postdoc at McGill that's moving to the Institute next fall. And this picture is meant to give you a flavor of the kind of a pictorial representation of the kind of setup we have in mind, which is how can we think of theories of gravity in the presence of time-like boundaries of finite size. And I should say, at any moment, please interrupt me with questions of any type. Okay. And so I'll spend some time motivating the problem because it's a non-standard topic in the field. These days. It's a topic that dates back to at least the 50s, in fact, under the guise of various names, including the name of relational observables. But the basic motivation from where we're coming from is that it occurs in often situations, many times, that the space-time, at large scales, the structure of space-time may exhibit no asymptotia. It's spatial or null infinity. For instance, cosmological spacetimes may have a compact Cauchy surface, which has no boundary at all, and hence no spatial or null infinity. Or you may have situations where the space ends in some singularity. This could be in time, for instance, if you have a Big Bang or Big Crunch type cosmology. Moreover, even if you had an infinitely large spatial slice, in cosmological scenarios, one could encounter horizons that shield any quasi-local observer from the large portion of space-time, rendering those pieces of space-time physically suspicious. Okay. In such circumstances, a more quasi-local description of the physical phenomena observed may be necessary. So that's the essential motivation. And what do we do? Mathematically. Indeed, just to add to this motivation, in our own world, provided that the cosmological constant is indeed constant and persists for some time, this would also apply if the vacuum we reside in is metastable, but perhaps not if it's slowly rolling. We're confined inside a very specific type of event horizon, which is known as the de Sitter space horizon, because all matter dilutes and the universe asymptotes to a pure de Sitter space, which has an event horizon. And in that case, although the future boundary, denoted by scribe plus over here, can be infinitely large, the physical phenomena experienced by an observer, which could be modeled by a laboratory on Earth, or the solar system, or the Milky Way, cannot access many phenomena that occur sufficiently far away. For example, if a star explodes in this region of space, it's forever causally disconnected from the experience of the quasi-local observer W over here. And so what are we to do in such a situation where we don't have a gauge invariant or diffeomorphism invariant observable like an S matrix or a correlation function at the infinite boundary of anti-de Sitter space, how should we even formulate the theory? And this is very close to home because indeed, whatever we deduce about the large-scale structure of the universe stems from light that we measure and analyze in a quasi-local scenario. We collect redshifts and luminosities from distant sources and reconstruct the large-scale structure of our cosmology based on that quasi-local data. It's not an S-matrix experiment. And so that's the basic tension in trying to build a theory of cosmology rather than a phenomenology of cosmology. And one idea that has appeared in several guises, as I said, that morally dates back to the 50s or 60s at least, is to try to append observations to a quasi-local time-like surface. So to define or decorate space with some time-like surface and see whether in relation to that, one can define observables. Now, this is a very challenging idea because the very setup is in tension with the equivalence principle and the invariance under general coordinate transformations. But it's an idea. Such entities exist, at least in the semi-classical limit, and that's how we actually make measurements to deduce the structure of cosmology. And these are a series of papers throughout the last 10, 15 years that have tried to explore this idea, always in an incomplete way. Yeah. Okay, let me pause to see if there are any questions in the motivation part of the talk.
You are sorry. Can I ask a question? Yes.
Of course.
Yeah. You assume the sitter is completely is the sitter, not transient de Sitter, not the sitter that eventually, not the dark energy type.
Yeah. So this problem is most pressing. So here, this purple line is meant to denote some initial condition. It could be a big bang of the universe. So I don't assume that it's the sitter in the far past.
Right.
But I do assume that the universe has a sufficiently fast acceleration in the future that it produces causally disconnected spaces.
Okay.
That doesn't have to be de Sitter. It could even be more aggressively accelerating, depending on the equation of state of the cosmological fluid that drives the acceleration. But de Sitter is an example of that.
Is that, yeah, that's fine. Thank you.
Yeah. Okay, so I consider this question to be very important because ultimately it may be tied to how we're supposed to formulate a theory of cosmology beyond effective field theory. Now, before moving on to some mathematical results, I should also say that this idea of adding time-like boundaries of finite size in physics has appeared in several other contexts in the history of physics. In the 80s, York, in very elegant work, considered the problem of a black hole surrounded by a box subject to Dirichlet boundary conditions, mostly in the spherically symmetric sector. And in an attempt to understand better the peculiar thermodynamic properties of the Schwarzschild black hole, such as its negative specific heat. In the stretched horizon picture, which people like Damour and others explored, Price, Thorne, many people explored, it was imagined in part for calculational reasons, but it's also a conceptually very interesting proposition, that we should replace the horizon with a stretched membrane that lives very close to the null surface of a black hole horizon and try to formulate physical quantities that reside on this stretched membrane. And the quantities that appear are reminiscent of dissipative phenomena in ordinary physics, such as the Navier-Stokes equation, which a portion of the Einstein equations reduces to along this type of null surface. This was the fluid picture, the membrane picture of gravity that was initiated in the 70s. And people continued to explore and made remarkably precise in the context of ADS-CFT much later. Jacobson, also in a very thought-provoking paper, re-expressed Einstein equations in terms of the local thermodynamics of horizon quantities in an interesting paper. So all this to say that we are not unfamiliar with time-like surfaces in gravity, and of course, there's the obvious one, which is the boundary of asymptotically anti-de Sitter spacetime, which has become very prominently studied as of the inception of the ADS-CFT correspondence. And so such time-like surfaces have been pervasive in our study of physics. And so one would imagine that there's a lot of mathematical machinery behind this story, which we'll see surprisingly is not the case. But let me try to re-express now the problem in a slightly more concrete way from the perspective of general relativity. The perspective of general relativity, one question one may ask, which seems natural, is whether we can formulate a well-posedness problem, one with good uniqueness or existence properties from the perspective of the theory of partial differential equations, on a manifold M, a four-dimensional manifold, which has a boundary of a time-like boundary, so it has one direction, which is time-like, and moreover will demand, and here we distinguish this type of boundary from the ADS boundary, that this is a boundary of finite spatial slice. In other words, if we intersect this boundary at any constant time at any spatial slice, the volume of sigma, the volume of the intersection of the spatial surface with the full boundary is a two-dimensional spatial manifold of finite proper volume. That's what we mean by finite spatial slice. Okay, and so the question is whether if we try to formulate general relativity in such a context where we have some four-manifold with this boundary, and this is not a physical boundary, there's no tensionful object that lives on this thing. This is a mathematical boundary. There's no energy density localized on this boundary. It's just a place where space ends and we have to do something to our fields at that point. So we would have to append some data to this boundary, as well as standard Cauchy data in this space-like surface over here that cuts through the manifold all the way up to the place where it intersects with the time-like portion of the boundary. Okay? And to contrast this with established results in general relativity, for example, if we had a theory with no time-like boundary, but instead a complete spatial boundary, sigma, like we do in the context of asymptotically flat space, where we have an infinite spatial slice, where we append physical data in the form of the induced metric and the extrinsic curvature, we know, thanks to work of Choquet, Brouat, and Guéroc, and Christodoulou, and Kleinemann, and others, that we can do this with good uniqueness and existence properties, and even good stability properties. And so the case of a complete spatial Cauchy surface is a very well understood case, particularly in general relativity with the positive and vanishing cosmological constant. And there's also results in general relativity where we try to define data on a complete intersection of null slices, N1 and N2, and we try to fill the boundary by appending data on these infinite null slices. So you'd imagine that there's a host of results for the case where the boundary is of this nature. But curiously, this is the case that is least understood in the literature of mathematical general relativity. Let me pause again to see if there are any questions. Okay. So I hope the question we're asking is clear, and the motivation behind the question, I hope from a physics point of view, is also clear. Just to reiterate, the question is, does there exist data on the boundary of our manifold, which we'll call W, which is the intersection of the time-like portion and the Cauchy, this portion here of the Cauchy surface? Does there exist data that we can append, geometric data built out of pieces of the metric, leading to existence and or uniqueness properties that are good for the solution developed in the remainder of the manifold M? I should also say that the way I've drawn the picture, it looks a lot like I'm trying to put gravity in a box. But you could also view the manifold as the complement, where we try to, and this is more relevant for cosmology perhaps, where the manifold we want to develop into is the outside of the box, rather than the interior. And so the immediate instinct that we may have is that we could try to set up a Dirichlet problem. In fact, for the Yang-Mills equation and the Klein-Gordon equation, in a similar setup, it's known that the Dirichlet problem, where we fix the value of the field along the timelike boundary, as well as the standard Cauchy data of the field, so it's a profile and its first time derivative along the Cauchy surface, leads to a good evolution equation in the interior. And so that's true so much so for the Klein-Gordon field as it is for the Yang-Mills field, provided we treat, in the Yang-Mills case, the zeroth component a little delicately. So one could ask whether one can formulate the Dirichlet problem in the context of general relativity, whereby along this timelike boundary, we fix the induced metric at all points on the timelike portion of the boundary, and the space-like portion of the boundary, we fix the spatial induced metric and the extrinsic curvature, like in the standard Cauchy problem, as well as a compatibility condition at the corner where the two data sets meet. The question is, if I fix this data here and here, I can, whether there exists evolutions of this data in the interior and whether they have any uniqueness properties. This is the kind of question we may ask. And this question attempts to formulate or prove things about this question appeared in the early 2000s, as late as the early 2000s, in a paper of Friedrich and Nagy, and then they were pushed significantly by Michael Anderson at Stony Brook and Zhongzhang Yan and Anderson also. And these papers are the Euclidean version of this problem. So you can ask this problem, I should say, both in Euclidean and Lorentzian signature. In Euclidean signature, this problem was discussed in Anderson's paper in 2006. And in Lorentzian signature, the state of the art is really a paper from 2 years ago, amazingly, for a problem that seems so foundational in general relativity. And from the physics literature, these type of results were imported into a more friendly language in physics in a very nice paper of Witten and a paper that we wrote also. Witten's papers in Euclidean signature, our papers in Lorentzian signature. And so I will discuss now the Lorentzian case. Please ask me about the Euclidean case if I don't say anything, but essentially the picture carries through in both Euclidean and Lorentzian signature, although the mathematics is a little different because of the elliptic versus hyperbolic nature of the differential equations. In any case, Ann and Anderson, in a paper in 2021, I believe, I can't remember the exact date, but not too long ago, proved the following for the Dirichlet problem. They proved that if I append the boundary with generic Dirichlet data, namely a generic induced metric on the timelike portion, plus the Cauchy data, for generic data, the problem does not have good existence properties. In other words, even if I did find a Dirichlet data set that does satisfy all of the constraint equations on the boundary and fills the manifold in a good way, if I slightly deform it away in some direction by modifying the induced metric in some region, it's no longer guaranteed, and in fact, generically, it won't be the case that there will be a solution in the interior. Moreover, they show in the same paper that when you do find data that does permit the development of solution in the interior of the manifold, that this data in no way is guaranteed to uniquely fix the nature of the solution in the interior of the manifold. And there can be instances where you have an infinite degeneracy of solutions given a unique, one given set of Dirichlet boundary conditions.
Dionysios, can I ask a question at this point?
Yeah.
Does this mean that you don't have in general a DS-CFT correspondence in such geometries, or?
I wish we could formulate that, the DS-CFT correspondence, in such sharp terms. The DS-CFT correspondence, in fact, would be more, the way I understand it, would be more compatible with data living on a complete spatial slice, because the idea of the DSCFT is that you have an asymptotic de Sitter boundary and you formulate some type of theory on the infinite future boundary, which is a complete Cauchy slice.
Okay.
And so this is the problem with, if you will, from the motivation I gave with the DSCFT, is that it's still a very global perspective of cosmology, because it deals with data that cuts through many horizons.
Right.
Here we're trying to do a more local version. Now, what could happen is that if we progress with this problem, we could find interesting data that lives on the timelike boundary that could have a structure that's interesting and also conformal-like. And so it would be a different class of ideas, not unrelated to those. Anyhow.
Thank you.
Okay, yeah. Okay, so the Dirichlet problem in gravity, unlike Yang-Mills and the Klein-Gordon equation, seems to be difficult to deal with. It's not clear, in other words, that this Dirichlet data is the way to go if we want to add a little world tube to GR. Okay, and so let me give you some comments about these two results. The reason why there's no generic, there's no guarantee that generic data will lead to existence is that along the timelike boundary, we have to satisfy one of the constraint equations that stem from Einstein's equations. And this constraint equation involves the Ricci scalar, but it also involves the square of the extrinsic curvature. K is the trace of the extrinsic curvature. So the extrinsic curvature tells you roughly how the surface moves radially in and out of the interior. So it's sort of like the exterior derivative of the induced metric, whereas R is a function of the induced metric on the timelike surface. And the fact that you have something linear in R but quadratic in K, if you vary these equations, leads to, if you do a small variation around the solution of this equation, leads to an equation where you have delta R, but you have things like K delta K. And so the way they prove it is that they say that one might find situations where both K and delta K are very small. So these could be sort of flat, what they call standard Minkowski corners of your solution space. And in such corners, these terms are quadratically small, whereas this term over here is only linearly small. But the equation delta R equals 0, where you vary the Ricci scalar as a function of its metric, is an equation that doesn't generically have solutions. It's unusual for a metric to have vanishing Ricci scalar on a three-dimensional space. And so it's a highly constraining equation that doesn't allow for it seems, a large class of variations of the boundary data. This is in contrast to what we know in ADS-CFT in the asymptotic boundary, where these variations would correspond to variations in the sources for the dual stress tensor of the CFT. And it's crucial that we have a regular functional of the boundary sources, because we take variational derivatives of the on-shell action to produce correlation functions of the stress tensor. And so if we had a highly irregular functional of the sources, we wouldn't have some of the basic dictionary of ADS-CFT working very well. And so this is quite distinctive to the case of finite boundaries. And the reason is that in asymptotically ADS, the nature of the metric becomes very rigid because of the Pfefferman-Graham expansion of the asymptotic structure of metrics in ADS, and doesn't allow for this generic variability that I'm discussing. So this is one of the reasons why it's difficult to impose Dirichlet conditions, and this is in contrast to the Yang-Mills case, where the gauge constraints in Yang-Mills are linear rather than polynomial. As for the non-uniqueness, an example of the non-uniqueness that gives a little bit of intuition is a case where you can study the problem at the linearized level. So imagine you have the linearized approximation to general relativity, and you study a situation where you have Minkowski space in the interior, and you embed the surface in Minkowski space in the simplest conceivable way. So in the corner, it just looks like you put a little box, and you have Minkowski space in the interior, and the box has a flat wall and no time dependence. And you might imagine that in such a situation, if you linearize the Einstein equations and try to solve the linearized Einstein equations for gravitational perturbation, which vanishes, whose profile vanishes at 0 time along with its momentum, and also vanishes for all at the whole time-like boundary, yeah, that its induced metric vanishes, the variation of the induced metric vanishes across the time-like boundary. You might imagine that the only solution to that is still the empty Minkowski solution. However, amazingly, even if you start with the Minkowski vacuum and turn on a linearized perturbation where you fix the induced metric to vanish on the time-like boundary and have vanishing Cauchy data on the t=0 surface, so that the momentum and the field vanish, one finds infinitely many solutions that satisfy this data, because there's components of the metric, and namely the components in the orthogonal direction, for example, h, x, x, that are not sufficiently fixed in the Dirichlet problem, and physical solutions can leak in through those components. Again, this is not something that happens in Yang-Mills, and many of the solutions that are degenerate locally look as if they're pure gauge solutions. However, we must remember that when we formulate GR on a manifold with a boundary, the diffeomorphism parameter xi nu has to obey boundary conditions itself. And so a solution that looks like pure gauge, but is built out of a diffeomorphism which does not satisfy the boundary conditions at the boundary of the manifold, cannot be called a pure gauge solution. It's a physical solution. It's a zero mode that is physical in the theory and can leak in and change the data without obstructing our seemingly restrictive boundary conditions. In other words, the Dirichlet problem is not stringent enough to allow the leakage of locally pure gauge modes at the linearized level to enter our system, even though we thought we had fixed all pieces of the time-like manifold. And this is at first very surprising. Okay, so let me pause to see if there's any questions about that. Okay.
And
This is meant to
this will be also the same in the Euclidean formalism?
There will be an analogous version of both statements in the Euclidean formalism, indeed. And in the Euclidean formalism, they were proved much earlier, because in the Euclidean formalism, you don't need to worry about the Cauchy surface.
Right.
If you have a Euclidean manifold, all you have is some boundary, which is space-like, and that's it. It's just the data on that. Here we have to worry about waves coming in and out, this corner over here, which might carry its own corner modes. And so that's the reason the Euclidean results came before the Lorentzian results.
Okay.
Yeah.
Thank you.
Yeah. Having said that, I should say that there could be special configurations. For example, if we carve out a spherical cylinder in Minkowski space, for which these zero modes can be killed due to global constraints on what diffeomorphisms are allowed. So that's one of the drawbacks of that list, is that they give genericity arguments, but they're not constructive. And so there could be exceptions, and we should be cautious of that. Okay. So at this point, I've discussed a negative result, and so now we can move on to discuss a positive result. And the positive result is that conjecturally, so in Euclidean signature, this is proved, but in Lorentzian signature, it remains a conjecture with evidence, significant evidence, and it's proved at the linearized level, which is the following: that if instead of the Dirichlet problem on this little tube that we have, we fixed what I'm calling curly H here, which is the conformal class of the induced metrics, that is to say, the induced metric up to an overall conformal factor, so the conformal class. And instead of fixing the full metric, I removed the scalar degree of freedom. Instead of that, I fixed the trace of the extrinsic curvature as well, so that I fix the same amount of local data as before on the timelike portion of the boundary. And then I fix the Cauchy data in the standard way, so the induced metric and the extrinsic curvature along the space-like portion. The conjecture is that when we fix the conformal class of the induced metric on the timelike surface, as well as the trace of the extrinsic curvature on the timelike surface, plus the Cauchy data on the spatial surface, we indeed do get a well-posed problem. And evidence, this statement can be essentially established at the linearized level. And I should say it is somewhat reminiscent of the type of boundary that lives near the boundary of ADS, because there's a way to think about the boundary data of anti-de Sitter space as if it was indeed a conformal class. And this statement has been proven in Euclidean signature. And just to give you a flavor of why this data does a better job, if we go back to the constraint equation that was giving us trouble before, if now we release the conformal mode of the induced metric, this equation will become a partial differential equation that the conformal mode has to obey. But we haven't fixed it. So a priori, it becomes a question of whether that partial differential equation admits solutions. And this is how they establish the good existence properties for these boundary conditions. They show that the class of that partial differential equation is one that admits indeed solutions. Okay. A drawback of this approach is that once we release the conformal mode of the induced metric at the boundary, we no longer have control over the size of this tube. And we may want to have control over the size of this tube if we want to keep the framework quasi-local. To some degree, one can control the size of the tube by controlling the trace of the extrinsic curvature, but it's not quite the same as controlling the size directly. So that's an interesting point. You have, something's got to give. Gravity seems to want some sort of breathing space in order to be expressed in a more quasi-local way. Okay. And there are many open questions that arise when we ask this. I'll discuss some results that follow by imposing these boundary conditions, but you may immediately ask yourselves whether anything is known about the mathematical structure of boundary observables. For example, if we have correlation functions on the boundary that are subject to these boundary conditions instead of the Dirichlet problem. And little is known about these, whatever axioms such correlation functions may be subject to. Okay. But the lesson here is that there's at least one data set that we can define for GR on a manifold with a boundary that seems to have at the classical level and hence at the semi-classical level, if we do perturbative quantization, good features. And this is a statement that is not more than 5 years old. This is a recent result, which is why we're revisiting the problem now. Okay.
Excuse me, Dionysios, are you able to say anything about the definition of a perturbative scattering matrix if you have quantum fields in these space-times?
Good question. Yeah, so that goes along so what this means is that not yet, okay. But you could naturally imagine not a perturbative scattering matrix, but a perturbative collection of correlation functions. Right. That are subject to this conformal structure, and maybe these correlation functions themselves have to have a conformal structure. Right. And so your question about DSCFT, ironically, might be a question that makes sense here as well, except now it would be a CFT constructed from these type of correlation functions.
Very good.
Yeah. Thank you. But before we ask that question, there's an even more basic question we should ask, which the mathematicians don't tend to ask, which is what about the dynamical stability for these boundary conditions? Right. You see, along with existence and uniqueness, the physicist, we must also ask as physicists about stability. The mathematician is less interested in that to some degree because, well, it'll go where it goes, and it's about local properties of the equation. But we felt it important to study the dynamical properties of this as well. And I'll report on that in a moment.
Thank you.
Yeah. Okay. I should also say that though it wasn't understood, the significance wasn't understood. I did find one context in the literature where these boundary conditions. Well, there's an old context of York in the 70s where he discusses very briefly these conditions, but they did also appear in the fluid gravity correspondence because people were trying to, like I said earlier, define Einstein's equations on a timelike surface very near a horizon. And it was observed in some papers that when this horizon is compact, the attempt that was made in these papers to impose Dirichlet conditions led to an obstruction in solving the Einstein equations when the surface was very near the null surface. And it was proposed in these papers that one should release the conformal mode. I was part of that literature, and I can tell you that I don't think, at least we didn't appreciate the significance of the result. But it was evidence of the non-existence property of Dirichlet. Okay. So what I'd like to do now, this is sort of the second half of the talk, is apply these boundary conditions to standard quantities that we tend to compute in physics to see whether anything changes in a qualitative way. Bearing in mind that if this tube is stable enough or sensible enough, it might be a natural starting point to define a collection of cosmological observables or an auxiliary step in achieving that goal. Okay. And so we can start in Euclidean signature. And the question I'd like to address here is what happens to the paradigm of black hole thermodynamics if instead of imposing Dirichlet conditions, we impose these conformal, I'm going to call them conformal boundary conditions. What kind of black hole thermodynamics do we get? Okay. And so the object we need to compute in Euclidean signature is a priori, we'd like to compute a Euclidean path integral. Of course, we generally don't know how to do that, but we can employ the saddle point approximation as we do for the Dirichlet case, and compute an object which will be a function. So we'll take the boundary to be an S1 times an S2 in Euclidean space. We'll fill it with a Euclidean black hole solution, so it'll cap off. And the S1 is meant to signify the thermal circle, the Euclidean thermal circle. But because we're only fixing the conformal structure of the metric at the boundary, really the size of the thermal circle should be measured in units of the size of the S2. So it's the ratio of the size of the S2 to the thermal circle. That's the conformal notion of the temperature. And we also have to fix the trace of the extrinsic curvature of this S1 times S2 embedded in the 4D manifold in order to fix the data, the conformal data. And in doing so, the type of boundary term we need to append to the Einstein action to render it well, so that it has a good variational problem will have a slightly different form than the standard Gibbons-Hawking-York term. It'll have a different coefficient. What one finds in doing so is that there are two black hole solutions that obey these boundary conditions, as well as the thermal vacuum, which has no black hole at all. That's reminiscent of what happens in the Dirichlet problem and also in the ADS problem. And as we vary the temperature, there's a type of transition at low temperatures. One of the two black holes, which has positive specific heat, as high enough temperatures, one of the black hole solutions dominates the thermodynamics, whilst at low temperatures, the thermal vacuum dominates. That remains true for these conformal boundary conditions. But one can take a large temperature limit as well in this problem. In other words, a small beta over r, where r is the size of the two-sphere. A limit where beta over r is very small. And one can compute the entropy in this limit. So that's a high temperature limit. Small beta is high temperature. And one finds that the structure of the entropy, the leading order in the high temperature limit, takes the following form, which is strikingly different from the form it takes in the Dirichlet problem, where this tends to a constant up to 1 over temperature corrections. And I find this formula fairly interesting because its dependence on temperature is quadratic, which is the type of behavior three-dimensional scale invariant theory or conformal field theory obeys at high temperatures. But in addition to this, there's a dimensionless prefactor that's very large, which is given by 1 over g Newton times k squared. The units of the extrinsic curvature is 1 over length, And so since this is external data that specifies the theory, the combination G Newton times K squared is a dimensionless number. And in conformal field theory, at least, the coefficient that goes in front of T squared, in ADS CFT, this would be something like N squared, the number of gluons of the dual CFT. Here is replaced by this 1 over G Newton K squared. And the reason I'm emphasizing this formula is that if you were studying ordinary flat space without any boundary at all, there would be no analog of this K, and there would be no way to form such a dimensionless quantity. Because in flat space, there's no, at least in the gravity sector of flat space, there's only a dimensionful, the theory only has one dimensionful quantity, which is the Planck length, which is different, say, from cosmological theory, where you have the Planck length and the cosmological constant scale, and you can form a dimensionless quantity. So even though we've built a problem in gravity with vanishing cosmological constant, we've managed to produce a large dimensionless number, which may have significance in the quantum theory out of K and G Newton. Okay. So for those of you familiar with ADS-CFT, this would be something like N squared, where N is the rank of the group of the dual CFT. And so one might postulate that in flat space subject to these boundary conditions, this constitutes the number of degrees of freedom in the microphysical description. And that would be an interesting formula to either find a way to rule out or give further evidence for. Okay. And the other quantity that, as I promised, I wanted to report on is the dynamics of the vacuum. Yeah. So the previous slide was about black holes, and we did a Euclidean thermodynamics problem. Here, I'd like to talk about the vacuum stability problem, which is the natural, once we establish uniqueness in existence, the natural question that we need to understand. And the setup that we studied in a recent article is the following. We will, as our vacuum, take Minkowski space, okay? So, and we'll use polar coordinates. Okay, and we'll consider the case where the radial coordinate goes from 0 to some value r, such that we have a boundary for the vacuum, which is S2 times r plus because we have to start at some t equals 0, and so it's a half interval. And the question is now, if this is our vacuum, you might naturally suppose that this is the vacuum, and we turn on some linearized excitation. So we'll fix the timelike boundary to be the conformal round metric on S2, yeah. So we'll fix the boundary to be this following metric over here. So minus dt squared plus r squared d omega 2 squared, where r is the radial, the size of the radius at this point. And we'll fix the metric to always be the conformally equivalent to this metric. And we'll fix the trace of the extrinsic curvature to be essentially 1 over r. That's what it turns out to be. And any perturbation we excite in the interior will be such that its evolution cannot disrupt our conformal boundary. Okay, so that's the linearized problem that we'd like to solve. So we'd like some perturbation, but whatever the perturbation is, we have to impose that it obeys the boundary conditions of our problem, because generically it'll affect the boundary metric and the trace of the extrinsic curvature, and hence it's not a physically allowed perturbation. Okay, so that's the linearized problem we'd like to solve, whether perturbations that obey the boundary conditions are well behaved, whether they grow, whether they don't grow, and so on and so forth. And the method we use to solve these linearized dynamics will be through the Kodama-Ishibashi treatment of linearized equations, where one splits using the SO3 symmetry of the background one splits the linearized metric into a vectorial spherical harmonic and a scalar spherical harmonic component. And one studies the boundary, both of these will obey a linearized Einstein equation, and one has to impose boundary conditions on them. And we'll also decompose the modes in a frequency space. Yeah, so they'll have some spherical harmonic part and some radial part, and which we require to be smooth in the interior, some spherical part, and a frequency. And the question is, upon imposing the boundary conditions, whether there's any allowed omegas, yeah, that will now have to obey a type of algebraic condition due to the boundary condition. That what kind of omegas are permitted in our problem, in our initial boundary value problem over here. Okay, it's just like studying fields in a box, but a slightly more elaborate version. Yeah. Hopefully the setup is clear. If not, let me pause to see if there's any questions. If not, I can proceed to just report the results. In the vector harmonic sector, so those linearized gravitational solutions built out of the vector spherical harmonics, which have a vanishing divergence, one finds that there are a collection of allowed frequencies that satisfy the boundary conditions. They all live on the real axis. They're evenly spaced, and it's very reminiscent of the problem of a particle in a box, where you have a discrete real spectrum. And this happens at each value of the angular momentum L. For the scalar sector, however, in addition to this family of real box-like modes, for each value of L, one finds a quartet of modes, two of which have positive imaginary part and two of which have negative imaginary part. And as L increases, the real part grows linearly in L, and the imaginary part grows as the cubic root in L at large angular momentum. And so we've encountered now a collection of modes. Remember, we have e to the I omega t. If omega has positive imaginary part, this leads to a behavior that grows. Not just grows, though, it also oscillates, because you have e to the L to the cubic root times ILT. And so we have to investigate further, and this is ongoing work, what the fate of these growing modes is. At the level I'm presenting it, what they indicate is that there's certain configurations that lead to a breakdown of the linearized approximation. I should say that in the context of anti-de Sitter space, there's a lot of work on growing modes that whose endpoint is believed to be the formation of a small black hole. But here we have to investigate the problem further to see what happens, because there's a possibility that these modes also cause the boundary of the tube to grow. So some of these modes indeed give rise to a time dependence of the size of the conformal factor, which is not fixed by anything. Okay, so there's an interesting structure in any case in the linearized theory. And it goes to show that though we have uniqueness in existence, we have to be very careful about the dynamical development of this theory. Are there any questions at this point? Okay, I should also say one more thing. The analysis that was done here was done for a constant trace of the extrinsic curvature. And we also analyzed the possibility of giving some time dependence to the extrinsic curvature at the boundary. And in doing so, we found that if we tune the trace of the extrinsic curvature of the boundary in certain ways, we can remove this exponential dependence at the cost, perhaps, of tuning the boundary data in a specific way. And now I'll just make some quick remarks because I think I don't have much time left, which is that this problem, in addition to the case lambda 0, given our motivation, it's very natural to study this problem at positive values of the cosmological constant. And in fact, we've initiated a systematic study of that case as well. And here you might hope that if the world tube is such that the interior of the space has a cosmological horizon, some of these growing modes could dissipate by falling through the horizon, and that stability properties might improve. Now, why would one wish to do so? Again, the existence and uniqueness issues carry forward to the non-vanishing lambda case for finite size manifolds. And also, it's known that if we put a Dirichlet tube in a de Sitter universe and study the specific heat of the cosmological constant in this setup, it's negative definite. And so there's no good thermodynamic properties. And one would like a situation where we have positive specific heat as well. Perhaps remarkably, or at least fortunately, if we put a tube in a de Sitter universe subject to conformal boundary conditions instead of Dirichlet conditions, one indeed finds that for certain values of the trace of the extrinsic curvature, which vary the sort of size of the tube, one can find a positive of the specific heat for the cosmological horizon. And as far as I know, that's the only context in which it can have a positive specific heat. And so it seems to be a friendly world tube. Moreover, in the de Sitter case, because we have a de Sitter horizon, we can study a particular limit, which is interesting, where we take the boundary of the world tube to approach, like I said before, the cosmological horizon, and study the kind of physics that occurs there. And because of the fluid-like behavior of gravity near horizons, indeed, one can formulate many of these questions in a fluid dynamical language, which there's shear modes and sound modes. And many of these modes really now constitute Navier-Stokes type behavior. In the other limit, where we take the size of the tube to be very thin, what we recover is a type of world line limit, where we probe the physics of de Sitter space along a thin world tube or world line in the limit inside of space-time, which is this initial motivation. But now a world tube where we can meaningfully append data and measure the phenomena with respect to if we could compute something like a correlation function. Okay. And so this is a very novel piece of mathematics that we can use, it seems, to study these kind of quasi-local questions. This, in part, might lead to further insight into puzzling features in Euclidean de Sitter space, just to make a more conceptual point, which is that there is one quantity in de Sitter space that people discuss often, which is called the entropy of the de Sitter horizon. And the way it's calculated, this was proposed by Gibbons and Hawking in the 70s, I think, or the 80s, is they say, take a theory of gravity with positive cosmological constant, go to Euclidean signature and consider a path, like we do for black holes, a Euclidean path integral. But the de Sitter space in Euclidean signature is a sphere. It's a maximally symmetric positive curved space. And so we have to do quantum gravity on a Euclidean sphere where there are no handles or boundaries or thermal circles. And so it's physically very difficult to understand what this quantity is. Just to give you the formula, the claim of Gibbons and Hawking is that this path integral, which semi-classically is the path integral of the Euclidean Einstein theory over all metrics, is in fact equal to the exponential of the quantum de Sitter entropy that includes all the one-loop corrections. And indeed, this quantity, though elusive, is diffeomorphism invariant, gauge invariant, and field redefinition invariant. But perhaps by adding a boundary to the Euclidean theory and then viewing the sphere as two manifolds glued at the boundary, we can provide further physical sense to this elusive sphere calculation, which would be very valuable because the entropy of de Sitter might be an important quantity for our own universe. In fact, the entropy of de Sitter space, the value of the entropy of the de Sitter space is a way to express the cosmological constant problem in a dimensionless way. Yeah. Because the entropy goes like 1 over g lambda, and so it's 1/10 to the 122 or so. Okay. This is a reiteration of the Gibbons-Hawking postulate that their claimed entropy, it's a highly speculative claim because there's little evidence for it. The claimed entropy of the de Sitter horizon is this peculiar path integral on a sphere, and it evaluates the 3 pi over lambda g, which, as I said, is 10 to the 122, which is the same value that puzzles us in the cosmological constant problem, but now expressed in terms of this information theoretic quantity. And the absence of a boundary in the sphere makes this puzzling to understand physically.
Dionysios, can I? If you accept the cosmological de Sitter where you have a constant Hubble, then of course you can define an observer-dependent temperature, the h over 2 pi. In this. So the question is, of course, is your approach valid for the cosmological de Sitter with a constant Hubble parameter, or you need modifications?
So here in the most concrete form of the problem, one imagines a universe which has equilibrated into a pure de Sitter universe with small fluctuations. This is the setup here. One could try to deform that setup and generalize these formulas, but it would be good to understand perhaps the cleaner setup first. The problem with the de Sitter temperature is that unlike the black hole temperature in asymptotically flat space or anti-de Sitter space, where you can measure that temperature with respect to a rigid reference frame, which is the boundary of space, and unambiguously declare what it is. For the de Sitter temperature, in order to explain what you mean by that, you need to introduce an observer.
Yeah.
And introducing an observer is not, we run into these issues of relational observables, diffeomorphism invariance. And so perhaps a way to unambiguously define what we mean by it is to introduce these well-posed tubes.
Right.
And in doing so, we may get a more thermodynamic understanding of this elusive entropy.
Right.
That's part of the fantasy.
Right. Thank you.
Yeah. And yeah, I should say that this given entropy in more recent literature, people have been as even more provocative and declared that it's equivalent to the dimension of the Hilbert space of quantum de Sitter. But all of these notions require a way to be qualified, in a way to be physically understood. And so I think perhaps if we have if we understand sort of pieces of the sphere path integral that can be then glued together, we may understand a little more clearly what the physical content of this, and this will be helpful in understanding the degree of freedom content of quantum de Sitter space, and perhaps in consequence the limitations of effective field theory, which is an important motivation of this whole work. Okay. So the outlook then is that there are surprisingly new avenues in GR, holography, Euclidean gravity to explore more finite features in quantum gravity. There's much left to explore. I don't think we have a clear picture at all, especially if we wish to connect all these different pictures in these new type of boundary conditions, which are not very well understood. And ultimately, this might be a method or a direction to explore to get a clear understanding of the role of an observer in quantum gravity. Thank you.
Ευχαριστούμε πολύ, Διονύση. Πολύ ενδιαφέρουσα ομιλία. Να σταματήσω μισό λεπτό την ηχογράφηση. Ωραία.